You know, one of the most fascinating things about the world is that we're surrounded by phenomena we think we understand until we really stop and ask why. Take fire, for example. We see it every day.
It cooks our food, warms our homes, powers engines. And yet, if I ask you a simple question, why does fire burn? The answer isn't quite as obvious as it seems. Uh, it's tempting to say, well, that's just what fire does. But that's not an explanation. That's just naming the mystery. So if you look up closer, when something burns, it's not just disappearing into nothing. That's Maya. Atoms rearrange, energy being released, light and heat pouring out. It's a kind of invisible dance between oxygen in the air and the material itself. The remarkable part is this dance follows precise rules of physics and chemistry that we can actually understand. But here's where it gets really interesting. The reason it feels hot, or hurt you, the reason it glows, it all comes from tiny interactions at a level so small we can't see it, yet so powerful it shapes our entire experience of the world. Right? Instead of just accepting that fire burns, let's ask the deeper question. What does burning really mean? And as we dig into that, we might find that something as ordinary as a flame is actually one of the most extraordinary things in the universe. You know, one of the most fascinating things about the world is that we're surrounded by things we think we understand until we really stop and ask why. Take fire, for example. It's so familiar that we almost stop noticing it. We light a match, turn on a stove, sit around a campfire, and the pole feels completely ordinary. Not there. But if you pause for a moment and ask yourself a very simple question, why does fire burn? You find that the answer isn't nearly as obvious as it first appears. Most people would probably say, well, fire is hot, so it burns. But that's not really an explanation. It's just restating the observation in different words. It's like saying water is wet because it's wet. What I'm trying to understand is what's going on underneath, what is actually happening that creates that heat, that light, that sensation we call burning. Right. Now, if you look closely at a flame, it doesn't look like a solid thing at all. It flickers, it moves, it changes shape constantly. That's your first clue that fire isn't a thing in the usual sense. It's a process. Something is happening. What we call fire is a rapid chemical reaction, a kind of energetic interaction between the material that's burning and the oxygen in the air around it. At a microscopic level, the atoms in the material, say the carbon and hydrogen atoms in wood, are bonded together in a particular way. These bonds hold energy. When the material gets hot enough, those bonds start to break and the atoms become free to rearrange themselves. The oxygen atoms in the air are eager to combine with them, and when they do, they form new bonds, stronger ones. And here's the interesting part. When those new bonds form, they release energy. Not just a little bit, but enough to keep the reaction going. That released energy comes out as heat and light. Jet derivative atoms move faster, which causes more bonds to break and more reactions to happen. So you get this kind of chain reaction. Cells are says that as long as there's fuel and oxygen, almost like a conversation between atoms, where one reaction encourages the next. But then you might ask, why does it feel hot? Why does it hurt if you touch it? That has to do with how our bodies interact with that energy. The heat from the fire is really just fast-moving particles and electromagnetic radiation transferring energy into your skin. The molecules in your skin start vibrating more and more. And when that vibration becomes intense enough, it disrupts the structure of your cells. That's what we experience as burning. The light glow of flame is another fascinating piece of the puzzle. When atoms and molecules get excited, literally excited, in a physical sense, the electrons move to higher energy states. But when those electrons fall back down, they release energy in the form of light. That's why flames can appear yellow, orange, or even blue, depending on the exact conditions and the materials involved. So what looks like a simple flame is actually an incredibly complex interplay of chemistry at front of us, right in front of us. The remarkable thing is that all of this follows precise, predictable rules that scientists have spent centuries trying to uncover, test, and understand. And yet, even with all that knowledge, there's still something deeply striking about the fact that a tiny spark can unleash such a magic transformation, turning solid material into heat, light, and invisible gases, all in a matter of moments. If you think about it a little more carefully, I'm almost strange about the way we casually accept fire as part of everyday life. We strike a match and expect a flame. We turn a knob and expect heat. Yet inside that expectation is a chain of events so intricate that if you didn't already know it worked, you might find it hard to believe at all. Imagine for a moment that you had never seen fire before. A piece of wood, something solid, something you can hold in your hand, and then under the right conditions, it begins to glow, to crackle, to transform into something else entirely. Light without being a light bulb, heat without being a heater, and it slowly disappears while producing smoke and gases that drift away into the air, almost as if the material is being taken apart and reassembled into something you can't quite see. What's really happening is that the atoms in the wood are not fixed in place the way they appear to be. They're constantly moving, vibrating, interacting. At ordinary temperatures, those motions are relatively gentle, and the structure of the material holds together. But when you add enough energy, say from a spark or friction, you push the system into a new regime. They get to move more violently. Bonds begin to break, and suddenly the whole structure becomes unstable. At that point, oxygen from the surrounding air enters the picture. So oxygen is a very reactive element. It wants, in a sense, to combine with other atoms like carbon and hydrogen. When the conditions are right, these atoms collide with enough energy to overcome the forces holding their original structures together. They rearrange, forming new molecules like carbon dioxide and water vapor. Now here's the subtle but crucial part. The new arrangements are more stable than the old ones. And because of that, energy has to go somewhere. Vanish. It's released. That release is what we observe as heat and light. That's essentially moving from a higher energy configuration to a lower energy one. And the difference shows up as the energy of the flame. This is why fire can sustain itself once it starts. Its energy released by the first set of reactions is enough to trigger the next set and then the next. As long as there's a supply of fuel and oxygen, the process continues. That fire is alive, but it has this self-propagating quality that makes it feel almost that way. There's also something interesting about how sensitive the process is. If you remove just one ingredient, take away the oxygen, for instance, the whole thing stops almost immediately. That's why blowing out a candle works. You're not destroying the fire directly. You're interrupting the conditions that allow those reactions to keep happening. And then there's the color and shape of the flame itself. A candle flame, for example, has different regions, each telling you something about what's happening inside. That's vaporizing. Where the wax is vaporizing, the temperature and conditions are different from the outer regions where complete combustion is taking place. The colors shift depending on how efficiently the fuel is burning and how much oxygen is available. All of this is happening simultaneously in a delicate balance. The flame exists only because these processes are continuously feeding into one another, energy breaking bonds, atoms rearranging, new bonds releasing energy again over and over. a dynamic system that only appears simple because we've seen it so many times now. If we keep digging into this question, it starts to reveal something even more interesting, not just about, but about how we understand the world at all. Because when we ask, why does fire burn? We are really asking a deeper question. What does it mean for something to burn in the first place? Burning is something we use to describe a whole collection of experiences that you feel, the light you see, the damage it can cause, the transformation of material into ash and gas. But none of those things by themselves fully capture what's going on. They're just different ways our senses interpret a much more fundamental process happening at a level we can't directly observe. At that deeper level, everything comes down to interactions between particles, atoms, electrons, and the forces between them. Those interactions produce something as dramatic as a flame has to do with how energy is stored and transferred in matter. Chemical bonds are like little packets of energy holding atoms together in specific arrangements. And when those arrangements change, the energy has to be redistributed. What's especially fascinating is that the energy released in a fire was not created at the moment the flame appears. It was already there, stored in the chemical bonds of the material. But it's revealing energy that has been quietly sitting there all along, waiting for the right conditions to be released. Idea back even further. It leads you into questions about where that stored energy originally came from. Quite old. The energy was captured from sunlight through process like photosynthesis. Made to rearrange molecules in the air and soil, storing energy in the structure of its cells. When the wood burns, you're not just seeing a chemical reaction, you're seeing sunlight captured long ago being released again in the form of heat and light. That gives a kind of connection to the broader universe that isn't obvious at first glance. It's not an isolated phenomena. It's part of a chain of energy transformations that stretches formations. They back out again. It's just one moment in that ongoing cycle. There's also an interesting point about how we perceive all of this. That our senses are tuned to pick up certain ranges of energy. Visible light, for instance, or the thermal sensations we interpret as heat. But the process itself involves far more than what we can directly feel or see. Principal gases being produced, microscopic collisions happening at incredible speeds, and energy transfers occurring in forms we don't consciously notice. So when we say that fire burns, we're really compressing all of that complexity into a single, simple idea. Here, of course, it helps us navigate the world, avoid danger, and make use of fire in practical ways. But it can also hide the richness of what's actually taking place. And that's one of the remarkable things about science. It allows us to take something familiar, something we might otherwise take for granted, and unpack it layer by layer. That depth of structure and meaning that isn't obvious on the surface. A flame, which might seem like a simple, everyday object. We go into the behavior of matter and energy at the fundamental level. In that sense, asking why fire burns isn't just about understanding fire. It's about understanding how nature works, how energy moves and transforms, and how even the most ordinary experiences are connected to processes that reach far beyond what we can immediately see. And if you push this question just a little further, it begins to challenge something even more basic, our intuition about what is solid, stable, and permanent in the world around us.
Because
When you watch something burn, what you're really seeing is matter losing its familiar form, almost as if it were never as solid as it appeared to be in the first place. Take a simple piece of paper. Stable, continuous, and unchanging when you hold it. But the moment it catches fire, that sense of permanence vanishes. The edges curl, it darkens, it glows, and then it begins to break apart into ash and invisible gases. What was once a single solid object becomes something fragmented and fleeting. But with our ideals is that the solidness we experience is not an absolute property. It's a kind of temporary arrangement. The atoms in that paper are held together in a delicate structure by forces that are strong enough to give it shape under normal conditions, but not strong enough to withstand the intense energy of a flame. Once enough energy is introduced, those forces can no longer keep the structure intact. At a deeper level, even the atoms themselves are mostly empty space. Their structure is defined by a tiny nucleus surrounded by electrons moving in regions of probability rather than fixed paths. Stability of matter comes not from rigidity, but from a balance of forces, electromagnetic interactions that keep electrons bound, and quantum rules that prevent them from collapsing into the nucleus. When fire enters the picture, it disrupts that balance, not by destroying atoms, but by rearranging them. The identities of the atoms remain the same, but the way they are connected changes completely. Habitual carbon atoms that were once part of a complex organic structure become part of simple molecules, like carbon atom form water vapor, but it doesn't vanish, it transforms. And yet to our senses, it feels like destruction. The paper is gone, the shape is gone. What remains is unrecognizable compared to what we started with. This is one of those cases where our everyday language doesn't quite capture the underlying reality. We say something is burned up, as if it has ceased to exist when in fact it has simply changed form. There's also something intriguing about how quickly this transformation can occur. Conditions. A slow, stable structure can become unstable almost instantly. A small increase in temperature can trigger a cascade of reactions that accelerates rapidly, turning a quiet process into a dramatic one. Appeal to initial conditions is part of what makes fire both useful and dangerous. And then there's the question of control. Learned over thousands of years how to manage fire, how to start it, sustain it, and extinguish it. But that control is always conditional. So maintaining the right balance of fuel, oxygen, and temperature. Change one of those factors, even slightly, and the behavior of the fire can change completely. Which makes this especially interesting is that the same fundamental principles apply in many other contexts. Where the idea of energy is stored in bonds released through transformation, and driving further change is not unique to fire. It appears in countless processes throughout nature, from the metabolism in our bodies to the reactions that power stars. So when you watch something burn, you're not just witnessing an isolated event. You're seeing a specific example of a much broader pattern, a pattern in which matter is constantly being rearranged, energy is constantly being transferred, and stability is always relative, depending on the conditions at hand. And the more you look at it that way, the less fire seems like a special case. And the more it becomes a vivid illustration of how dynamic and ever-changing the physical world really is.